All right. Tonight's program is particularly relevant to the work we have been doing on site. So tonight we have Newlin Gristmill's Executive Director, Tony Shahan, who will be our speaker for this evening's program, Turning Water to Power, How Water Systems Work. So I will go ahead and turn things over to you, Tony.
Thank you for having me tonight, Laura. I will get started here and is that working for everybody? Okay. Well, humans seem to actually be drawn to water. And I was looking at this and there are multiple questions out there. Is it because of the mystery of what lies beneath? Is it because we depend on it for survival? Is it the beautiful scenes like we have in this picture? Or is it something deeper, possibly even at the genetic level because of this long association with water? And in fact, if you think about it, we use it for everything in life, from nourishment to transportation, for our rituals, for recreation, for art, all of these things. But tonight, I want us to step back a moment and look at water as a tool. How have humans been using water through history? And if we look at some of the early things, like this rice mill, Korean rice mill that's in Gifhorn, Germany, it's a simple system. This cam system has been powering mills throughout history. Still places in the world that it does that. It's a simple system of making an automatic mortar and pestle. But this is not a primitive technology. It may be rudimentary, but this is a system that has played a lot. And when we go back and look at these, when did we start using water power? We think about it as something that in America was used from the beginning, but we go back and the first written description is actually made by Vitruvius, a Roman architect engineer from the 1st century. He actually describes a water wheel, a vertical water wheel, all the gearing, a set of millstones, and a hopper being used to grind flour. And at that point, it seems like it's a well-established thing. And in fact, those pieces are the main pieces of the mill, even into the 19th and early 20th centuries. Even the water wheel, if you look to the picture of the right, it's a simple paddle design, much like this one. It's a wheel that has a series of paddles that you put water running against it and it makes it turn. What I find fascinating is at the same time that they're writing these descriptions about this water power, this is one of the primary sources of mills. This is actually the bakery at, Pompeii. And they have all millstones that are either human or animal powered. And this is a primary source for the cities to get their grain ground and turned into bread. Well, within 200 years, this is what we see the Romans doing. It's one of the largest mechanical power centers in all of the ancient world. 16 mills set in 2 parallel designs. And they are doing everything from using the topography, but also recycling water. So they only have to have half as much. They literally are using the water that it would take to run 2 mills to run this operation. And this is the kind of technology that makes the expansion of the Roman Empire and its continued growth possible. But it wasn't just in flour. We see in this 3rd century sarcophagus a carving of a stone saw that's all water powered. And if you see the illustration in the upper right hand corner, it shows you exactly what this would have looked like if you set it up and made it work today. And it, again, isn't just the small operations. This is a Roman water wheel that was excavated in the early 20th century in a copper mine in the Iberian Peninsula. This is part of a 50 water wheel system that they use to not only process the ores, but also pump the water. And in fact, this wheel is described as pumping water over 80 meters up into one of the drainage canals to get the water out of the mill or the mine. And mining itself is at the core of all the early writings in the medieval world and early modern world about water power. As early as this 16th century drawing, they have made a reversible water wheel that you literally have two sides. You have an upside and a downside so that you can lower and raise things with the same wheel. And here's one in a mining museum in Rammelsburg near Niedersachsen, Germany. It's about a 40-foot wheel. It's a huge wheel in this mine. This is taken from above it because it was the only angle I could get to where I could see most of the wheel. It's about 100-year-old wheel, and it's just like the one you see in the illustration. It has buckets going both directions with a forward and backward. Because they're pumping the water out, but they're also pumping from other locations to use to operate their water wheels that are running pumps. It's almost a self-running system. One of the interesting things about this one, though, is that if you look at all the white in the one side of the wheel, that's actually mineral deposit. And I've seen other places in this mine as we walk through of systems that they were completely encased in minerals. So I'm wondering if that's part of the long preservation of this one as well. They also applied it in medieval cities where they were trying to figure out ways to serve the needs of these populations. Basic mills are not necessarily easily there, or the type of mill that we think of are not necessarily easily set up in a city. You need space, you need elevation change. But in the rivers, you had big rivers, lots of current, and they basically started building mills on boats, tying a water wheel onto the side of them. And then you could actually bring grain in by boat and haul out flour by boat and never had to leave the river, which was one of their main transportation systems, which is also why these boat mills became so important. Because the early water powered mills that they tried to build on the European rivers kept getting torn out because they were blocking transportation, which is a key transportation network were these major rivers. But all these cities started having these little operations everywhere where they could stick them. The photo in the lower left is actually a fulling mill for processing textiles. And the wheel would have been underneath it in that canal so that as the tides came in and out of that canal, or the flow of the water, it would have actually made that wheel turn and they've been able to do work as they needed it. But this is one of 7 mills that were in operation at this site at one time by the 15th century. And a boat mill was everywhere. I mean, there's still a few of them scattered throughout Europe. But they were 2 boat bodies. One had a mill built on it. The other one acted like an outrigger or a pontoon with the water wheel going between the two. And we know that there were actually boat mills on the Delaware River, on the Ohio River, and many of the other rivers in this area. And it basically was a paddle wheel. And instead of being propelling the boat forward, they would actually anchor the boat and let the water run through it and move the paddle to power all the machinery inside. Other than the fact that it was on a boat, there was nothing different about these mills than any other mill. But water power has several problems. We learned that in 2020 as I repeated, we have too much water and we have flooding. They are connected. We had a massive amount of rain, everything floods. Water powered mills do not work unless you put them in floodplains. And if you do that, they will flood. But they also have problems of, this is a picture from out west right now with too little water. Drought is also a major issue. But water power is also limiting because you can't move. It's not like having an engine that you can pick up and move somewhere else. If you move it, it won't work anymore. So it's very connected to specific regions and geography. And siltation is another major problem. We're basically creating with our water systems big stilling chambers because we back up the water, we try to slow it down and control it. As we do that, any silt that's suspended in those creek waters just falls out and fills up areas. This is actually a turbine along the Delaware River underneath a mill that has completely silted in. There's probably 6 foot of silt in that area just to try to get it open to be able to operate that mill again. Okay, so what is a typical water system? Well, I can give you a list of parts of a water system, but as I hopefully will show you in some of these, there isn't one that's typical. And that's because a water system is a character defining feature of any mill site. And when I say that, what I mean is it's built into the landscape. Usually, we've actually even referred to it here as a machine on the landscape that is for converting potential energy in water to mechanical energy in the mill. And it's a series of dams, gates, canals that bring water from one place to another. But it has to be built specifically into the topography in which it's set, or it won't work properly. And your basic parts of a water system is you have to have a source of water. You need a dam. You need to have a control gate or a head gate. You also need a mill race, and that's just a canal to carry water in. And in that mill race, there's 2 parts. There's the head race, which is what carries water to the mill, and a tail race, which is what carries it away. You need a trash rack in there to keep the debris from blocking up your wheels, or even more importantly, not getting caught in the gates so you can't close them or open them sometimes. And you need a flume and a flume gate. That's what helps you accelerate the water right before it enters the wheel and makes it go just a little bit faster and get a little bit more power out of it. And then you need a wheel itself to convert. And there's multiple kinds of those as well. I'm going to look at a couple of these quickly, but as I'm talking, I want you to keep note of the terminology may be different than you know, or you may hear me use interchangeable terminologies. And that may be because I'm looking at mills from different locations. Milling terminology is very much a regional thing, and they change. I've been in conversations with people where it took us 5 minutes to understand we were talking about the same thing before. But here's a couple of examples of mills that I've actually worked at. The Newlin grist mill, of course, it's somewhat unique because it has a dam here and it has a dam here. It's on the Concord Creek in the West Branch of Chester. It has a half mile long mill race carrying water to the mill. It does contain a spillway gate right here that helps protect the mill race, and it has a flume that's all underground. It's in a pipe that goes into a box in the mill, and then our tail race exits out here. One of the interesting features is the gate for the head gate is right here. And that's a telling thing because that should be right where the water enters the mill race, which means that this, we now know, is all silted in pond. And we believe that the original mill pond was several acres in size. Another mill that I worked at was the Greenbank Mill down in Wilmington. It too had two dams, had a large dam up here, a smaller dam here. But notice there's a control gate right here, which told us that this was probably the original dam. And the water bypassed it at some point. So they came back in here and rebuilt all of this with a new dam. They did put an overflow channel in to hopefully keep this from getting blown out again. But it has two dams, but for a whole different reason. They're still only drawing water off of Red Clay Creek. The one thing that this has that's somewhat unique is that it ran a sawmill site, a grist mill site, a textile mill site, and a woodworking factory site, all off the same water system. And a lot of these water-powered sites were actually developed without any mind of a mill. They built the power structure, and then the rest of it was kind of like we think of outlets, is once you have the electricity run, you can plug whatever you want to into it to run. And a lot of these mills were meant to be interchangeable as the industries changed. In that diversion channel area at Greenbank, when we were restoring this, we actually found another feature that I've only ever seen in the Delmarva Peninsula, but I'm sure it's all up and down the coast, is in areas that don't have a lot of bedrock, they would put floating beams in and then build their stone structures on top of those. And that floating beam would actually keep it from sinking into the land. Oops. This thing is super sensitive tonight. Topography. When the Europeans arrived into the New World, they knew about water power. They had centuries of experience. What they weren't necessarily expecting was the amount of capacity for water power that was in the New World. It was everywhere. And in fact, by 1840, there were over 14,000 water-powered mills working. And when the early colonists got particularly to the mid-Atlantic area, they had one great feature. It was this one right here. This is the fall line. It's the geological separation between the coastal plain and the Piedmont. It's an old ancient seacoast that has a steady fall. And what that does is it's perfect for being able to put mills in and run water wheels. One of the great things about the fall line, either it's a result of or it influenced, and depends on what historian you're talking to as to which one it was, is it either encouraged the development of major cities, because if you see, it goes through all of these major population centers, or they developed around what was going on. But here's a good example of why a fall line is so important. If you look at the river level is right here. And this river is actually a series of stepped ledges of stone and goes back several hundred yards to where the water level is actually this height. So that big difference right there. And it goes into a mill race, comes around, there's actually the spillway here, and then it goes into the wheel. Well, the distance between here and here, where the water goes into the wheel and where it exits, is called the head, and that's your potential energy. And by having this fall in elevation, you can stick a mill in, and in this way, you can actually put the dam further upstream, and your mill is at a higher elevation above the water. So if there is flooding, there's less chance of it coming into your actual mill building. This is also very typical of most sources of water in American mills. It's these little streams that you put dams on. However, it's not the only sources that they had. They also had several other little ones like this one. This is actually a subterranean river in southern Indiana. It's called the Cave Mill. And there's enough water that flows out of this cave that feeds the flume for the mill. This goes down and keeps, I think, about a 16-foot wide by about 2-foot deep stream fully flowing. Plus, about 100 yards above this picture, there is a intake for a concrete plant that's pulling all of their water for their operations above this. So there's a lot of water coming out of this dam, and they've come up with a really ingenious way of tapping into that and running 2 or 3 different mills. In fact, at the mill itself, this set of water system runs 2 different water wheels in the same building. This is another one where they found a fast flowing spring and they built a dam and they captured it, created a small lake, and you can run the mill all day with this and then leave it overnight and it will refill. That's how much water is flowing into it just overnight. One of my favorites that you see down in Virginia and the Carolinas a lot are standpipe mills, where either underwater or underground or under on the surface, they ran pipes. And the water would actually come from a lake that it was a much higher elevation than this. I'm not sure what's going on with this. Much higher elevation than the wheel in the mill, so that it acted like a water level. And when they let the water into the pipe, it would automatically rise up in the pipe and flow over to the wheel. They're really cool to watch because the water just looks like it's bubbling up. One of the biggest sources, and possibly one of the early sources that was tapped into, were the tides and the oceans. This is a tidal mill in the northern neck of Virginia. You see the water wheel shaft to the right. It's got a couple spokes still remaining, but as the tide came in, they actually went out and built this man-made barrier across a bay and or an inlet, and they would let the tide come in, fill that, close the gate, and then use the water. And then when the tide went out at a later point, they would actually get the water flowing out again. And there was a lever inside that allowed them to flip the switch, and they could use the water coming in either direction and the wheel turning whichever way it was. But tidal mills, actually one of the earliest mills to ever be excavated was in County Down, Ireland. And it was at a monastery site, and it had 2 separate mills. There was one built in 619 AD and one in 789. And it was a monastery, which fit one of the limitations of tidal mills very well, in that you have to work with the tides. So you have a change of power twice a day. This particular one is interesting because the earlier mill had a very large impoundment, and that's what you're looking at here, is this large impoundment. This opening here and here are this opening here and here, just for orientation. So it would have been here. It looks like they were probably gate openings originally. Mill would have been located here. They'd let the tide come in, close the gate, and then ran this out. Well, the second mill that they built in 789, they decreased the amount of basin by about a third, and continued to operate at least through the dissolution of the abbeys in 1588. So it was in operation for a long time. Now, my question is, why did they decrease the size? Did it have to do with a lack of need, a lack of manpower to do it? Or was there a threat from the water? Because this usually indicates structure. And it looks like they may have filled this area in to help protect the monastery site itself from being eroded away. One of the largest, actually the largest tidal mill in the UK is outside of London. This one mill has 3 water wheels in it and 12 sets of millstones, and has been around forever. This variety you see here was built in 1727, I believe, and continued to operate until 1940. They had to shut it down during the Blitz. But it is known in the record that there was a mill, a tidal mill, working on this site in the 1086 doomsday list. So they've been tapping into this for a very long time. But you don't necessarily have to have lots of water. This is at San Jose Mission in San Antonio, Texas. And the same indigenous technologies that have been used for centuries to bring water from the local rivers to irrigate farming were employed to create these little ditches and bring water into this mission mill. And the design is also equally ingenious because they built these basins on the outside of the mills that would fill up with water, create water pressure, and it would then push into the flume, which was restricted at the end, and created even more pressure to run against these wheels. And they were very efficient, as you'll see here. Not much water running there to make that work like that. So one of the big things we have are dams, and dams come in lots of sizes, shapes. Most people think of a dam like this. It's a large stone wall, lots of water cascading over it. But in fact, there are more dams out there that are like this, that are smaller, lower head. This is the one at Greenbank Mill, or I'm sorry, Newlin Grist Mill. And the stone section you see here is actually a spillway to let the creek water go over the top of it. And then it's about twice as long as this, with the other half of it being an earthen dam to impact, as I said, about 10 acres, we think, of water. Going through a book called the Book of Buildings, it was Mr. Livesey had been keeping records on 2 mills on the Wissahickon Creek in Philadelphia for about 50 years. And his maintenance records are 60% dealing with water systems and water damage due to flooding. We had a similar incident a few years ago when we came to work, and this is what we found in our main dam. The center section had washed out. We started looking at it and studying it a little closer. Pardon me. I found that the right-hand side was built in one period and the left hand was built in the other, and it probably failed where they joined the two together. But the right-hand side was built most likely with heavy equipment, machinery, probably around the turn of the 20th century. The left hand was smaller stones, very meticulously placed and held together. And in fact, about 4 foot up from the bottom of the dam, they put a row of stones that had slanting surfaces in, which then slanted everything above it, helping reduce the amount of front edge of that stone exposed to the water, so it wouldn't be washed out as much. And as we dug a little deeper, we found these stones in here that were set at 60-degree angles, one on top of the other, kind of like fish scales that help turn the water. We actually tried some of this, and it infilled with silt and protected that area tremendously. And once it was done, everything worked really well. Even with the big floods we had last year, we had a couple of stones that had to be replaced over here, but nothing in this area where we worked before dislodged. And we think it's because we were using some of those earlier techniques. Some dams were made out of wood, stacked. This one is actually a double wall, and then it has a slanted plank top on it. That's to help as the water comes in, it acts like a knife edge to cut through it, but it also allows trees and stuff like that to more easily go over the top and not be battering rams against the structure. Notice also the huge spillway that they have over on the left-hand side to help get the floodwaters away from the dam and also away from the mill to the right. Whenever you put a mill next to a dam, you have the potential for making it flood, or more easily making it flood. This is an interesting mill. Actually, this one is in Tennessee. And if you have any old film buffs, this is actually Sergeant York's grist mill from World War I fame. And they had a turbine in it, and the water would go through the turbine and spill out to the left-hand side there. But because they had a turbine, they were able to put a long shaft in to go all the way up to the mill and put that mill on piers to keep it out of the floodplain a lot further. At each one of these dams, you have some sort of head gate or control gate. They can be larger, complex structures. They can be smaller structures, like the one on the right. You can actually also see the curvature of that dam. Not all dams are straight. Some are convex, some are concave. There are even some that are V-shaped. And there are lots of different theories on what works best. That control gate becomes very important because it controls the amount of water flowing in, the volume, but it also controls the speed. One of the biggest issues that we deal with is erosion. And if the water goes through here more than half a foot a second, it will scour that out and cause significant damage. The other thing is volume. If so much water comes in that it overflows, it can erode out channels in our banks, in our mill race. So that's why they started putting in spillway gates. If you look at the one up here, you can see this height right here is the water level we want in the mill race. Gives us plenty of space. Anything over that will spill out and go back into the creek for people downstream. And they can be effective. You'll see this one actually has about a foot of rainfall that is built up on top of this, and it's taking it away very, very well, as a matter of fact. The interesting thing about spillways is they're always proportionate to the amount and the size of your mill race. Medium-sized one for a medium mill race, and then you have a tiny one for a tiny mill race. This is about 16 inches tall and 16 inches wide. So they're all built specifically for that case. Everyone has a trash rack of some sort. Otherwise, you can get sticks and debris built up and get so bad that you can't close your gate, which has happened to me before. And in the middle of a tour of mill experts, my water wheel gate would not close, and the water wheel just kept running. And there wasn't anything I could do about it until we got that stick out of the way. But the water's coming in to a flume then. And again, these are made out of stone. They're made out of wood. Some of them are small. Some of them are large. Some of them are actually iron, like the one on the right. This is in the Susquehanna State Park. It's a 32-foot diameter wheel, 3 foot wide, and a pipe brings water in. And this is a water box where the water fills up in here, and then the pressure makes it flow out evenly onto the wheel and consistently. So you don't get lots of changes in how the wheel's operating. There are large ones, and this is in fact very much like the one we're building for Newlin grist mill right now. And you have to think about, there's about a 5 foot by 5 foot by 80 foot long column of water in there. And the weight and pressure on that is massive. So it has to be built with heavy, thick framing to hold it together. And then the planking itself is 3-inch thick planking. So it's a significant structure. But not all of them, as we said a while ago, are that big. This one is a fairly small one, but it's intricate. And if you look carefully, you'll see this one was built to bring water from a lot of different places. And it was built so that the mill was set at a central location, and they brought the water to it overhead rather than trying to put the mill close to the water source. And that way they were able to bring them in from different ways and bring enough water to make it run. This is, in fact, the Mabry mill up on the Blue Ridge Parkway. So it's at the top of the mountain where you're not going to get a lot of fast moving streams. It's going to be a lot of spring and small stream. Again, there's the pipe. The pipe has become a friend of mills in the late 19th and 20th century. There's a lake on the other side of this road, flows underneath this and brings the water over to the mill. And then you get into some more complex ones. This is a textile mill in southern Indiana. And if you see, the pipe comes out of the dam in the back, flows down all the way to the left-hand side to a turbine. You see the small shaft running up into the mill. But in the middle, it actually has a standpipe that also feeds that water wheel and makes that wheel go. And the reason this is able to work is that standpipe is actually lower than where the water comes into the flume. And you notice that the pressure valve down below is wide open, letting some of that pressure out so that they don't pop the seams on things as well. It's the topography and the location on that topography that dictates everything about water wheels. Their size, their design, how the water gets to them. It's all about where the higher up you are, you have more head. The middle part, you have a medium head, and the lower section, you have a lower head. And there's water wheels designed for each of those. Low head wheel is also called an undershot wheel, has paddles on it. The water velocity strikes them and makes them turn. The breast shot, the water hits it about middle. Usually it means you don't have quite enough head to get up over the top. But you also see these, although they're a little bit smaller diameter wheel, they oftentimes are a lot wider. And that makes up for that. In effect, you've got two water wheels running in this one particular wheel. It gives you twice as much power. Then you have overshot wheels. They tend to be bigger around. They have to be at least 12 feet to be efficient usually. And they oftentimes be narrower as well. But there are also oddballs out there that we keep running into. This is a mill wheel in Northwest Yorkshire that has only one set of spokes. It's centrally located. Those buckets, which it's about 3.5 foot wide, are centered on those spokes. And the machinery in this mill dates to about 1717. We know that the wheels only last about 20 to 25 years, so we don't expect it to be that old. But it looks like what they may have done is what we call in the field is replacing in kind. So that if something wore out, they built it like it was and didn't improve it. This is a rural country estate out in the middle of nowhere. And it seems like it's probably a very early style of wheel, even if it may not be more than 100 years old. Then you have all your horizontal wheels. Horizontal wheels, also known as a Norse mill, is basically a shaft with a water wheel on one end and a millstone on the other end. Has a flume that concentrates the water, speeds that velocity up like we saw in that mission mill a while ago. This is one that actually has cups. And as you can see, the very little water, it's really efficient. And at the other end of it, we have the millstone working. One of the biggest drawbacks of these is the fact that you can only make your machinery run at the same speed as your water wheel. So unlike the gearing that we use oftentimes, there's no way to speed it up or slow it down. You can, however, take those horizontal wheels and make them more efficient. You put them in a tub, you concentrate the flow, and it increases their power. The pinnacle of this type of design is the turbine. It's a steel horizontal wheel in a metal case. Has these little slats down here. You put this in a big box, and see the box frame right here. This one's being disassembled. Put it in a box, and you put a big pipe like this one in that flows water straight in and fills it. And there are holes in the bottom of that box underneath those turbines, and all that water is forced out through that turbine. And as it goes through, it hits the blades on the shaft, and that's what makes it turn. And it's very efficient. The one thing about this is to make it more efficient, it requires a lot more water. And then you have what's called a flutter wheel. These are actually really cool in that they're vertical wheels, but they're really small diameter. This one I think has 5 blades on it. And they're really inefficient, but it requires a large amount of water, and it doesn't matter if it's inefficient at that point. This one's running a sawmill, and this box is nothing but a big column of water, and there's a slat across the back that when you open the gate, it just hits it all the way across. It's fun to watch. Once you have the wheels turning, though, you got to get that power out to the mill, and gearing is the best way to do it. We know that Vitruvius talked about this, using gears. And his mill would have looked very much like the one in the lower left-hand side. But what's interesting about these mills is there's no design for a second water wheel, or I mean, a second set of millstones. So you would have had wheels like this, where you might have a mill that has 2 wheels. What you don't see is that there are 2 wheels on this side of the mill and another one around the corner to the left. So as many millstones as they had to have a water wheel. And this exists until about 1680. And it wasn't until then that they came up with this simple lay shaft technology that allowed them to run a second water wheel, or I mean, a second millstone. From the gearing then, once they got that to where it was efficient, they figured out pulleys. And this is for a sawmill that had a huge, this is about a 12-inch wide leather belt that ran the entire sawmill above it. And then you've got all this water, and what you have left is for the water to go back to the creek. Most people do this in an open canal or a tail race. Our particular tail race here is a 210-foot long tunnel. And you see the engineers in here studying it at this point. Thank you all for coming out. I hope you have learned a little bit and got something out of this. Maybe you'll come back and start exploring water systems here at Newlin Gristmill. Any questions?
Great. Thank you, Tony. Yeah, if you have any questions, you can type them into the Q&A or into the chat, and we will read them out and try to answer them. Apparently you covered everything.
Either I covered it all or they're all asleep.
Well, if there aren't any questions, thank you everybody for attending tonight. We do have one more program in our Newlin series. And that will be on Thursday, September 22nd at 7 p.m. So another Thursday evening. Dr. Tara Trammell is going to be talking about the work she's been doing on restoring the iconic American elm to urban landscapes. So focusing back on nature for our last program of the season. You can register for that talk on our webpage on the Newlin series portion of the site, as well as you'll be able to watch the video from this presentation and the previous Newlin series that we've done virtually. So we also have a couple of big events coming up. September 10th is our Archaeology Festival, and October 1st, we have our Fall Harvest Festival. So make sure to get those on your calendars and be on the lookout for information about those coming up. So we've got thank yous and assurances that nobody is asleep, but I don't see any questions. So I will say thank you again for joining us tonight, everyone. And thank you, Tony, for a great presentation. And we hope to see you all at the mill soon.
Thank you all. And can I make one quick invitation to everybody to come out and see our millwright shop on Fridays and Saturdays, except for tomorrow we're closed. Thank you all.
All right, thanks. Have a good evening, everyone.